Good morning. Today we shall see one of the Fourier-based analyses in CFD, especially related to numerical stability. You may often hear the words, "This scheme is less dissipative," "This scheme is more diffusive," "First-order scheme is dissipative," etc. We shall see that is numerical dissipation, dispersion, and how to mathematically quantify it. We shall also see various ways to quantify this, followed in popular CFD books, and how efficient they are. We shall try to understand them visually, then we shall dive into mathematics. In this numerical simulation of the convection equation, the amplitude of the signal reduces over time. This reduction in the amplitude happened because of inappropriate numerical schemes or conditions chosen for this problem. The reduction in the amplitude is a pure numerical phenomenon. We call it numerical dissipation. In this simulation, you can observe oscillations are present. This is because different wave numbers in the solution propagate at different velocities. This we call as numerical dispersion. One of the popular ways to quantify numerical dissipation and dispersion is by using approximate dispersion analysis. It is a popular analysis used in several popular CFD and numerical books and several papers in leading journals. There were several papers completely based on this analysis in the 1990s, and you can find a few of these in recent years, or at least use this analysis. We shall see how to do this analysis and why I feel this analysis is incomplete and may be invalid. Up until now, I haven't come across any papers employing accurate analysis, with the exception of those utilizing Euler-time integration. In our upcoming videos, we will demonstrate how to rectify this. Since it's a subject open to debate, if you have any differing opinions, please feel free to share them in the comments section. One-dimensional linear convection equation is, using Fourier decomposition, we write the linear convection equation as, when we discretize the spatial part of the linear convection equation using backward in space gives. Applying Fourier decomposition gives the modified wave number relation. The modified wave number can be rewritten as, the first part of the equation corresponds to numerical dispersion, and the second part corresponds to numerical dissipation. Now we shall look again at the numerical solution of the FTBS scheme. The amplitude reduces and the bottom portion widens, which clearly indicates it has both dissipation and dispersion. Now, the real and imaginary part of the modified wave number is shown in the figure. The real part approaches 1, and the imaginary part becomes 0 when we refine the grid points. It says the numerical dissipation reduces to 0, and the numerical wave number matches with the physical wave number, so that their ratio is 1 when the grid is refined. We shall check this in the previous simulation using 100 and 1000 grid points. From this, it is clear that numerical error is reduced with grid refinement. These are the arguments given by researchers who use this analysis. Please note that I was also one among them a few years ago. Now we shall see why I feel this analysis is incomplete. We know the importance of the time step and CFL number in CFD simulation, but this analysis does not account for it. This we shall illustrate using the following example. In this simulation, we have used 100 grid points, but used different CFL numbers. As per the analysis, both were supposed to produce the same results because we used the same number of grid points. From this, it is clear that numerical dissipation is the function of the CFL number for this case, and not always a function of grid size. In the next test case, we used 101,000 grid points and used CFL number 1. As per the analysis, 1,000 was supposed to give a better result compared to 100, but both gave the same result. The spatial approximate dispersion analysis and modified wave number analysis are incomplete because it does not account for time discretization, which plays a crucial role in the numerical stability analysis. This can be overcome by spatial temporal ADR analysis. But I don't know why researchers still use this analysis even in the top 10 journals in applied mathematics based on the Web of Science ranking. Please put in the comments section if there are any mistakes in my arguments. Thank you for watching till the end. Have a nice day.